It was a difficult day today because I had to teach in person and then I have to come back to teach online. Okay. But everything is okay. So let's recall something. So we have a vector valued function. We have a vector valued function on an interval I. Right? So pictorially, we have a curve in space. And then we have the interval I. And let's call this AB. And as time evolves, a point in space would trace out a trajectory. Okay. So this is the time t. And we have the point R of t here. And then we call this curve C, the trajectory, capital C. And then last time, we actually computed the arc length of the curve C. So let me put down the formula for the arc length. Okay. Well, by definition, or actually not really definition. Definition plus some computations would give the arc length of the curve C. So it's the integral of f prime t squared plus g prime t squared plus h prime t squared. And then we take the square root dt. This is the arc length. This is basically the point where we stopped last week. Now, if you look at this integral, I can rewrite it in another form. Now, I have f prime t, g prime t, h prime t. So, when you differentiate the vector valued function, okay, then you are going to have f prime t, g prime t, and h prime t. And then you have the square root of the sum of the squares of the derivatives of the components. And that's actually the length of r prime t. So the magnitude or the length of the vector r prime t is equal to the square root of f prime t squared plus g prime t squared plus h prime t squared. It's not very good. Let me write this a little bit lower. Okay. So once you see this, then we can rewrite the arc length of the curve C. So the arc length of C is equal to the following. Is the integral from A to B of the magnitude or the length of the vector r prime t dt, which looks a little bit better, but they are the same formula. Okay. All right. Let's do one example. we are going to look at the same vector value function for the helix again. So R of t is given by cosine t times I plus psi of t times j plus t times k. Which is nothing but the following vector. So this is f of t, this is g of t, and this is h of t. Now, let's assume that t is between 0 and pi by 2. Okay. The interval in question is the one from 0 to pi by 2. So let me rewrite the formula again. Okay. Now, what's the graph of this vector value function? Well, I actually drew it very quickly on the first day of class.
Is it a helix?
It's a helix, yeah. I drew it on the first day of class, but I did it without all of you present. Okay, you still remember that the E-class was actually unstable and down. So let me draw it again for those who didn't see it. Now, let's try to look at the XY plane. Which means what? Which means that Z is equal to 0. In other words, T is equal to 0. Okay? And then I have cosine T and sine T on the XY plane, which is actually a circle. Okay. And then, of course, there's part of the circle behind the board. So it's something like this, the part that you cannot see. Now, when t is equal to 0, I have 1, 0, 0. I have this point.
Sir, I have a question.
Yeah.
So with the graph of the helix, can we also can we also like do this method where we graph the x, y, so cos t and sine t, so we know it makes a circle, so we know the base is a circle, and then since t keeps on increasing,
Yeah.
then we can just assume that it's a helix when we like graph it out and stuff. Like, would that be helpful, like when graphing?
Well, we have to be a little bit more careful. We have to look at the points or certain important points. Okay.
Okay.
Now, as t goes from 0 to pi by 2, let's look at the endpoint, pi by 2. Okay. Now, this tells us that the projection of the helix on the xy plane is actually a circle, right? Now, when we are up to t equal to pi by 2, now what is this point first? This is 1, 0, 0. We just saw it. And then this point corresponds to what? Well, x is equal to 0, y is equal to 1, and z is equal to 0. Okay, so we have that. Now, everything is within this cylinder. Okay, everything is.
Sir.
Yes.
Sorry, sir. So sorry to cut you off. I just have a question. So is 0, 1, 0 an actual point on the graph? Because if t equals 0, then that's not a real point, right?
Actual point on the graph. I am saying that this point is 0, 1, 0.
Okay, for like the base. Okay.
Right?
All right.
Now, t is increasing because time evolves. So it evolves from 0 to pi by 2. So when t is pi by 2, let's say we have the point for x equal to 0. Because cosine pi by 2 is 0, sine of pi by 2 is equal to 1. Is it? Yeah. And then t is pi by 2. And this point is a point in the helix. So you see that the helix is going up like this. And then it will spiral upward, as you said. But we are only interested in the part of the helix in this interval. Okay, so this is part of a helix. Okay. Now, the problem now is to find the length of this portion of the helix. Okay, let's call this C. And this is part of the helix, not the complete one. Okay. When you want to find the length of the complete helix, it's infinite, right? So we have to look at part of it. So you see, this point 0, 1, 0 is not in the graph. It's not in the helix. Okay. Now let's try to find the arc length of C. Okay. Now, how to do it? Well, we use the formula. So it's going to be the integral from 0 to pi by 2. Of the magnitude of the vector value function. Right? I don't use F, G, and H now. This is much more succinct and easier to remember. Okay. Now, we have to find the length of the vector. So we have the integral from 0 to pi by 2. Now, this course is very heavy in integration. So if your integration techniques are not strong enough, then this is really not a course for you, because somebody asked me about prerequisite. Okay, so it demands very skillful techniques in integration. Okay, but at this point, everything is still very simple. So we are going to integrate from 0 to pi by 2 of the magnitude or the length of the vector. And what is the length of the vector? Well, the first component is cosine t. So we take the derivative. So it's going to be minus sine t. The second component of r of t is psi of t. And when you take the derivative, you get cosine t. And the third component of r of t is equal to t. And when you take the derivative, you get 1. This is not absolute value. This is the length of the vector.
Professor, don't we usually use double brackets or?
Some people use double lines, but more modern textbooks and more advanced books simply use single lines. Okay. I still see some people use double lines.
Hello, Prof.
Hmm?
Is
Uh,
that
hmm?
one, or is that the number one that you wrote in the bracket?
Yeah. Why?
Okay.
The
No, I was just
derivative of t is 1.
yeah, I thought it was an L for a second. My bad.
No. Okay. Is 1. Well, if you like to use double lines, then you use double lines. Okay. But more modern usage prefer to use single lines. So we have to compute the length of this vector. So we have the integral from 0 to pi by 2. And then I have the square root of psi squared t plus cosine squared t plus 1. Okay, dt. But we all know what sine squared t plus cosine squared t is equal to 1. So we are going to have the integral from 0 to pi by 2. Of the square root of 2 dt. Right? Because 1 plus 1 is equal to 2. And this is a very easy integral to compute. If you compute it, you pull out this square root of 2. And then you integrate 1 with respect to t from 0 to pi by 2. So you get pi by 2. And the answer is pi over the square root of 2. So the length of this part of the helix is pi over root 2. Something unexpected. Okay, not a nice number. They are irrational numbers. Okay. All right. So much for arcane.
Sir.
Yeah.
So when you have a whole number, for example, just like the square root of 2, like for the integral, just like like little recap for about integrals, we can take out the whole number outside of the interval and just use it as a coefficient.
Well, when you integrate a constant, of
Yeah.
course, you can bring a constant out.
Okay. Okay. Perfect. All right. Thank you.
Well, even like this, a of f of x dx.
Yeah, we can take
Bring
out.
the constant out, right?
Okay. All right. Thank you, sir.
Okay, now I am going to another topic. Now, other than arc length, the length of the curve is certainly interesting. Now, there is another feature of a curve that's even more important. Now, if you have a curve, you want to measure how curved it is. And the quantity of the curving is what people usually call the curvature. So I am going to look at the curvature of curves in R3 or in R2. Okay. So first of all, let's take a vector value function. So let's say R of t. I am not going to write down the components this time. So R of t is a vector value function. Well, again, on an interval I. Okay. And we suppose that this vector value function has three properties. Or maybe two, because I combine 1 and 2 together. So this R of t is a vector value function such that R prime of t, the derivative, exists for all t in R. And furthermore, I want this derivative to be continuous for all t on I. Okay. So this is the first condition. In fact, there are two conditions here, but I combine them into one. Secondly, I want this derivative to be non-zero. Okay. Again, on the interval I. Okay. And I am going to look at this curve. You will see why these conditions are important in a moment. So let's look at 3 dimensions again. And we have a curve. Which may go outside of the board and go inside the board. It's not a plane curve. Okay. And this is the interval I. Fix a time t. And then there is a point on the curve corresponding to it. Right? This is the curve. Now, at this point, I am going to look at the tangent vector to the curve C at the point R of t. So I look at this tangent vector. Okay? It's a vector. It's the direction in which the curve bends. Okay? What is the formula for this tangent? Tangent vector. Well, the tangent vector to the curve C, which is the graph of R of t. At the point R of t, is given by the following. Is simply the derivative of the vector. Okay. So this tangent vector has a length and a direction. Correct?
Sir.
Yeah.
So what is so can you emphasize what that arrow is exactly? Like it's just the direction at which before it curves?
The vector.
Okay.
Okay.
And you're saying that this arrow is a derivative of RT?
Yeah.
Okay.
A tangent vector is.
Okay.
Right? Is the derivative of R of t.
Yeah. Okay.
R. Now, it has a length, it has a direction. But we are not so much interested in the length. We are more interested in the direction of the tangent vector. Why? Because we want to know how the curve bends at this point. Okay? So if you don't want to care about the length, then I am going to divide it by this length. All right. Well, it's not good to look at it like this. Otherwise, it's confusing. Let's say consider this tangent vector. And I am going to divide by this length. In other words, I normalize the tangent vector. Okay? So what is the length of this normalized tangent vector?
The arc length?
No, the length of the vector. Take the length of the vector. This is a number, right?
Yeah.
So when you take the length, so you have the length divided by the length.
Is it a unit vector?
It's a unit vector. What's the length? Is equal to
One.
what's the length of the vector?
The square root of f prime t squared. No?
You take the length. You don't have to care about this. This is a positive number. And then you have one number divided by the same number. What is it?
One.
One.
One?
One.
One.
Right. Okay. So I am going to denote this by T of T. Okay. So it's actually a unit vector. Let's say this is T of T. It has been normalized. So this unit vector always has length equal to 1. T of t always has length equal to 1. And now you understand why we need this to be non-zero. This is not equal to 0 everywhere. Otherwise, you cannot divide. Okay? Now,
Sir,
you have this tangent, unit tangent vector. We can,
sir,
yes,
can you go over how you got that equation? The T of t?
no, I define this, and that's it.
I think it's in section 13.2.
I let
Oh,
T
the
of
given formula?
well,
Yeah, the formula is in 13.2.
but that,
Okay.
that doesn't answer the question. He's asking me how I get this equation. This is the definition of T of t. The definition, well, that's why I said consider T of t, which is the derivative, the tangent vector, normalized. Okay?
Okay.
That's the definition of T of t. All right. Now, at each point on the curve, there is a unit tangent vector. And we want to see the rate of change of this unit tangent vector with respect to the arc length. So now I have the definition. Okay. So when we are at this length, we want to know the rate of change of the unit tangent vector with respect to an increase or a decrease in arc length. So I am going to look at the magnitude of the derivative of the unit tangent vector with respect to arc length. This is a vector. This is a scalar. So the whole thing is a vector. And we are going to look at its length. And we call this length kappa. Okay? I denote this length by the Greek letter kappa, which is a K anyway. Okay? But we call it kappa. This is what people usually call the curvature. Of the curve C. Which makes sense. It tells us that when we are at this length of the curve, how is the curve bending? What is the rate of change of the curve? And this is going to be measured by the direction. Okay. Now, this is the definition.
Excuse me, Professor. Just a quick question. So you denote the arc length with the letter S?
Yeah. ds.
Okay, thanks.
Okay.
DS, okay.
Yeah. Now, this is the definition of curvature. it tells us how the curve bends. But for calculational purposes, this is not too easy to use. And we are going to change this formula back to t, back to time. And we are able to compute the curvature of curves in spaces. And this is a good point to stop. Well, actually, I went over time.
Sir?
Yeah.
Can you explain the DS part? I'm a bit confused about that.
Well, it's the derivative. Well, this is one variable. This is another variable.
Okay.
You can always differentiate with respect to any variable.
But what does the like DS like represent? Like, is it like didn't you say it was the arc length or something?
What is dy dx? Dy dx. Same thing.
Oh, okay.
Okay, except here I use s.
Okay.
S is arc length. And x is the horizontal line.
Okay, so DS is the slope. Okay.
No, ds is actually the very small increment in the arc length. It's just like dx. The very small increment in the displacement along the x-axis.
Okay.
Same idea. Except that we are now more sophisticated because this is a vector. This is arc length. This is the arc length, not x, not the length of a small interval. Okay?
Okay.
All right. Now, still about the textbooks. I think the problem actually came from the bookstore. He actually puts the link to the book by Velo Reader, is it? I think it's Velo Reader, which is not the publisher. But I think it's still okay. You can still purchase separately the WebAssign.
Sorry, I have a question.
Yeah.
I didn't listen that. I mean, what small increase of DS?
Now, let's take a point X. Okay. And then you can look at a small increment. A small increment in X. And we call this length here dx. And when you increase x to x plus dx,
Okay, thanks. I understand.
time also increases.
Yeah.
Except that now we are more sophisticated. We are going to look at s. I will do more about this next time. And then you look at a very small increment, s plus ds. At this s, you have a unit tangent vector. At this x plus ds, you have another unit tangent vector. Now, the question is, how is the new unit tangent vector related to the original FS? And that's dTds. The same like dy dx over there.
Hello, sir.
Yeah,
I had a question. You were talking about the rate of change of the curve. And you were saying it's going to be determined by the direction of the tangent. Is that what you were saying, or
Yeah.
do I have it mistaken?
Yeah. Yeah.
Okay, thank you.
which makes sense anyway. Well, otherwise, how can you look at a curve and play with it? And then you just try to put a tangent vector there, unit tangent vector there, and see how it moves. Right? And that's the idea. Yeah. Okay. You use the unit tangent vector to find the change in direction of the curve. Or in other words, how the curve C bends when you increase the length of the curve.
Professor,
Yeah,
can I share my screen to show the university bookstore, York? I
Oh,
could not search.
I have seen it. Yeah. Yeah, I have seen it. Yeah.
Mm.
Oh, hi, Professor.
Everything is in E-class anyway. This is what they posted. But that's the correct also anyway. It's a shortened version of the blue book. But you still need to have the WebAssay anyway. And the WebAssay, I think, belongs to the publisher Cengage. I think Vilo Reader bought the book, and that's it. But I am going
Hi,
to.
Professor.
Well, actually, many students have bought the WebAssay already. Yes.
Hi. Hi, Professor.
Yeah.
So can I ask the website that I registered like last week, but I didn't see any homework or assignment in there.
Oh, I haven't given out any assignment yet.
Oh, okay.
I
Thank
will
you.
give the assignment on Friday. Okay, coming Friday. Okay, I have to do enough so that the assignment is more meaningful. That's the idea. All right.
Excuse me, Professor, I have another question.
Mhm.
So it's actually about the last lecture that we had when you showed us how you derived the formula for the arc lengths, and we used it today as well. When I took Math 1310, we actually were going through this topic about arc lengths, and the professor at that time provided us slightly different formula when it's the integral from a to b and the square root of 1 plus f of x squared dx, if I remember correctly, something like that. Does it sound familiar to you?
Can you repeat that again?
Yeah, so there's another formula for the arc lengths that I've learned before in Math
That
1310.
one, I think that one is for R2 anyway. Y
Yes.
equal to f of x.
Yeah, that's right. I was just wondering if,
Yeah, they are equivalent. You can actually reduce this back to that formula. Yeah.
okay, yeah, that's what I wanted to know. Perfect. Thank you very much.
Yeah,
Thanks.
Okay, so we stop here today. Okay, so see you on Wednesday then.
Bye, sir. Have a good day.
You too.